Welcome to the third lecture on RSET online lecture series of Special Electrical Machines EE402. Today we'll start with Module 5, Part 1, which deals with permanent magnet DC motor. References for this lecture is textbook on Special Electrical Machines by E.G. Janardhanan. Now, as we know, in a conventional DC motor, the main flux is produced by a stationary field system which consists of field winding, and we have to excite the field winding. But for small applications or small power or low power applications, for example in control system, this sort of excitation leads to lower efficiency due to high field copper loss. So for these type of applications, we replace the conventional field system or field winding system with permanent magnets, which thereby results in higher efficiency, less space requirement, and better cooling. Now moving on to the construction of a permanent magnet DC motor. It mainly consists of three parts: stator, rotor, and commutator and brush arrangement. So this is the stator frame on which we place the permanent magnet, and this is the rotor construction, which consists of slots, and inside these slots we place the windings, armature windings, and the end of the armature windings are connected to each commutator segments. So these are the commutator segments, and the circuit connection, external circuit connection, is taken through the brush arrangement. Now moving on to the construction of stator, it consists of a frame, stator frame, which is made up of magnetic material, and it serves as a return path for the stator magnetic flux produced, as well as it acts as the support for the permanent magnets. Now different permanent magnets used for the stator construction, different grades of alnico, which is an alloy of aluminum, nickel, and cobalt; ceramic or ferrite magnets, which are commonly used permanent magnets; samarium cobalt; and neodymium iron boron. Now these two figures are the examples of a four-pole system. The first figure is a four-pole York system with longitudinally magnetized permanent magnet. So here we are using 4 poles, 4 permanent magnets, 1, 2, 3, and 4, and a soft and core material adjacent to these will get also magnetized with south pole. Here adjacent to 2 north poles you get a north pole, then here you get a south pole, and here adjacent to 2 north poles you get a north pole. So this is a 4 poles longitudinally magnetized permanent magnet system. And here in the next figure, figure B, the permanent magnets are placed like this. 4 permanent magnets are placed like this. And along the thickness of the soft iron core material, you get magnetized. The permanent the iron core material gets magnetized due to the permanent magnet effect. Here you have north pole. Adjacent to the north pole, you get full north pole, and here you have south pole. Now these are the examples of two-pole York systems. Again, you are using two permanent magnets, and on the pole arc you get a you get the pole induced. Figure E is two-pole York with arc system. Here also you are using two permanent magnets, and on the soft iron core material you have pole induced. Adjacent to north you have north, and adjacent to south you have south pole. Now in details, the different permanent magnets used in stator. The first type of permanent magnet used is different grades of alnico, which is an alloy of aluminium, nickel, and cobalt. They are mainly used for high temperature application, and different grades are available for alnico depending upon their quality. Alnico 5, 7, and 9, and the grade number increases with the quality. Second type is ceramic or ferrite magnet, which is the cheapest permanent magnet available. Now, this has some property like linear demagnetization characteristics in the second quadrant of BH characteristics, and it has lower remanence, which is nothing but the maximum flux density that can be maintained by the magnet after being magnetized to a saturation at a specified temperature. Also, it has higher coercive force, and its performance is good up to 100 degrees Celsius. Now next is a neodymium iron boron permanent magnet, which is the latest member in the family of permanent magnet, and they have high energy stored per volume property, which makes them really attractive. And another type of permanent magnet used is samarium cobalt, which can be used for high temperature applications up to 200 degrees Celsius. Again, it has large remanence and high coercive force. Next is the rotor construction. Rotor or the armature is the part of a permanent magnet DC motor in which the EMF is induced and to which the external source is connected through commutator and brushes. So here in a permanent magnet DC motor action, for a motor action, external source or external power is provided through commutator and brushes to the armature windings, and back EMF is induced in the armature winding. There are mainly three types of rotor construction. One is slotted armature, second one is slotless armature, and third one is moving coil armature. The first type is slotted armature. So in this construction, the armature is made up of silicon or carbon steel sheet material. They are punched together and mounted on the shaft. Now armature has slots on the outer periphery. Slots on the outer periphery. So these are the armature slots. As you can see, it is on the outer periphery. Now these armature conductors, which are properly connected to form the armature winding, are placed in the slots. So the armature slots have armature winding. Now we usually use larger number of slots in order to reduce the torque ripple and electrical noise, and we again prefer odd number of slots in order to reduce the cogging effect. Now there is another method for reducing the cogging effect. As we know, it can be reduced by skewing the slots, which eliminates the interaction between the rotor teeth and pole. The machines which use ferrite magnet as the permanent magnet in the stator has the armature with thin teeth and wide slot. Machines which use ferrite magnet as the stator has its armature with thin teeth and wide slot. Now when we use thin teeth, it increases the flux density, and as the thickness of the teeth is reduced, more space will be available to house or to occupy the armature conductors. And the machines of this type, where we have thin teeth, is known as copper machine. And we have another type of slotted armature construction, and this is used where the permanent magnet is alnico. If the stator has alnico as the permanent magnet, in the armature we can use narrow slots and thick teeth. This type of machine is known as iron machine. Now next is slotless armature. In the slotless armature construction, the conductors are fixed on the outer periphery of the core, and the outer periphery doesn't have any slot. So this is a slotless construction. Now if you compare it with slotted armature construction, the effective air gap length is larger, and for the slotless armature construction, basically we use a alnico or a rarer magnet as the stator. It has the major advantage that it causes a reduction in torque ripple. Now next type of armature construction is moving coil armature, where the iron core material is replaced by glass fiber material in the armature, and it has advantages like low inertia and negligible iron loss in the armature since we are using glass fiber material. Now next part of PMDC motor is commutator and brushes. Commutator and brushes are used for energizing the armature winding from an external connection, from an external supply. So this is the external DC supply. Through the brushes, the DC supply reaches this point, and the commutator segments, which has the armature windings connected on it, will be energized through this external DC supply. Now the magnetic field in the air gap of the permanent magnet DC motor is heteropolar, and the EMF induced in the armature conductors will be alternating in nature. From the external DC supply, the current passes through the brushes, and it is distributed in the armature winding in such a way that a unidirectional torque is produced. Now the commutator segments are mechanically fixed to the shaft, and they are electrically isolated from each other and the shaft using some insulating material. Now the armature windings are connected to the commutator segments. Here you can see the connection. Shaft, clamp, commutator segment, and the riser. These all you have studied earlier in the DC motor construction. Now the brushes slide over the commutator segments. Brushes are stationary and they are fixed on the magnetic neutral axis M and A. Now for explaining the working of a permanent magnet DC motor, we'll take this figure. Here north pole of the stator is shown. Under the north pole you have a set of armature conductors where the current is flowing into the armature conductors, which is shown by the indication as cross, and due to the interaction between the current and the field, a force is produced, or each conductors will experience a force which is in the counterclockwise direction. Now let's see the working principle. Whenever a current carrying conductor is placed in a magnetic field, it experiences a force whose direction is given by Fleming's left-hand rule and whose magnitude is F equal to BIL, where B is the flux density, I is the current flowing through the conductor, and L is the length of the conductor. Now take this example. Here the armature conductors are carrying the current. The current direction is into the conductor and it is placed in a magnetic field which is produced by the permanent magnet. Now apply Fleming's left hand rule. Now Fleming's left hand rule states that if the thumb, forefinger and middle finger of your left hand are stretched mutually perpendicular to each other, and if the middle finger indicates the direction of induced EMF or the current, induced current, forefinger indicates the direction of field produced by the stator, then the thumb will indicate the direction of force experienced by the armature conductor. Now by applying this Fleming's left hand rule, we will see that on each armature conductor, the direction of force will be acting downwards. Now due to the interaction between the current and armature current and the magnetic field, the conductors will experience force. These forces will add up together in order to form a unidirectional torque. In this example, it is in counterclockwise direction. Now once the armature starts rotating, a back EMF will be produced in the armature winding. Why? Because the conductors cuts the magnetic flux produced by the stator field, and as a result an EMF will be induced, and that EMF is known as back EMF. The direction of back EMF will be opposite to that of the applied voltage. The electrical energy for overcoming this opposition formed by the back EMF is converted to mechanical energy, which is developed in the armature construction.